And now we begin our third and final video over our class notes. Unit 1, page 7. This is class notes 1-7, and in the previous two videos we talked about the properties of matter. Extensive and intensive is one way to classify a particular property. But matter itself can be classified based on its physical properties or its chemical properties. Physical properties, every substance has its own unique physical properties. In other words, when we look at all these properties down here, texture, odor, color, malleability, ductility, boiling point, melting point, density, all of these properties can be used to identify a particular substance because every unique substance has its own set of physical properties. They can be similar to other substances, but not exactly the same. Likewise, each substance has its own type of unique chemical properties. So every substance reacts in its own special way with other substances. When it reacts, we're talking about chemical reactions taking place. In chemical reactions, you produce substances that substances undergo chemical changes, and you can represent those with equations. And we mentioned a lot of these symbols that you'll frequently see, or things that you'll frequently see added to chemical equations to clarify what must happen in order for that reaction to occur. But we've been talking about chemical properties and physical properties. Why? Because we've been mentioning that the alchemists sought to turn ordinary metals, ordinary base metals like lead and copper, into our precious noble metals such as silver or gold. But we know the alchemists could not transfer copper or lead into silver or gold. Why couldn't they do it? It's because trying to turn one substance into another substance when we're dealing with elements is impossible to do in a chemical reaction. Chemical reactions cannot be used to change one element into another element. Elements are already the simplest form of matter. When you take any substance or any form of matter and break it down into the substances which make it up, the substances which make it up are called elements. Elements make up other things. Gold, silver, copper, and lead are all elements. They can join together to form another compound, but you can't take other elements and change them into a different element in a chemical reaction. Why is that? Chemical reactions involve electrons. Electrons are found in the electron cloud surrounding the nucleus of an atom. The electron cloud is mostly empty space surrounding the nucleus. It contains tiny, tiny little electrons. Electrons are the part of the atom that engage in chemical reactions. In a chemical reaction, atoms can share electrons. That's called a covalent chemical bond. Electrons can be transferred from one atom to another. That's called an ionic bond. Those are some bonds that can exist during a chemical reaction. Chemical reactions involve electrons which are found in the electron cloud. But the electrons have nothing to do with who a particular element is. It's the nucleus. It's what's inside the nucleus that determines what an element is. The nucleus is the dense inner core of an atom containing protons and neutrons. Those are big particles. Those are big subatomic particles. The electrons are very, very small. But the nucleus has protons and neutrons joined together. The protons and neutrons are not involved in a chemical reaction. It's electrons that are involved. When an atom is having a change in its number of protons and neutrons, it's not a chemical reaction, but rather a nuclear reaction. When an atom has a change in its number of protons and neutrons, the nucleus itself is changing, and so will the identity of the element we are talking about. The atom can be changed. But chemical reactions do not involve protons and neutrons. They involve the electrons. So we've been starting to get into the topic of what happens in a chemical reaction. In a chemical reaction, atoms bond chemically with other atoms to form new substances. As mentioned, chemical bonds involve electrons. What are electrons? They're tiny little negatively charged particles orbiting the nucleus in the electron cloud. The number of electrons influences its chemical stability. Its chemical stability, not its nuclear stability. So chemical stability tends to exist in atoms. Atoms are trying to get 8 electrons for most atoms. The smallest atoms only need 2 electrons in their outermost electron cloud, or outermost level of their electrons. We call that the valence. The valence is the outermost level. Most atoms want to get 8 electrons in their outermost level. The smallest ones only need 2. Hydrogen, helium, lithium, beryllium. They become chemically stable when they have 2 electrons. This is the tends to be in nature what's a stable number of electrons. How do they get that stable number of electrons? They bond. If an atom transfers electrons to another atom and the one that's getting the electrons ends up with 8, it forms an ionic bond and you end up with more stable atoms. A covalent bond is where they share 1 or more electrons and the 2 atoms are sharing them. In this type of bond, in a covalent bond, the electrons are shared right between the atoms. They're kept in the space between the atoms. They're restricted to the space between the atoms. Those electrons are said to be localized. The electrons are kept in the space between the 2 atoms. A third type of bond is called a metallic bond. In a metallic bond, they also share electrons, but the electrons are not held fixed between the space of the 2 atoms sharing them. In fact, the electrons are free to wander from atom to atom to atom. All the atoms in the substance are sharing the electrons. The electrons are free to move, so they're delocalized. So if you're local, you're held in place. If you're delocalized, you're free to move to a new locality. This is what happens in chemical reactions. Electrons are transferred or shared. The number of electrons an atom has is changed, but that doesn't change the atom into a different element. In order to do that, you would need a nuclear reaction. Nuclear reactions actually change the nucleus. Again, the nucleus has 2 particles. The protons are a positive particle, much, much larger than the electrons. It's the number of protons that determines the identity of an atom. If an atom has 1 proton, it's hydrogen. If it has 2 protons, it's helium. If it has 3 protons, it's lithium, etc., etc. If you look on the periodic table, you'll see the number of protons listed in the particular place on the periodic table. That is because that number of protons, called the atomic number, identifies that element. Here we're looking at a periodic table of elements. The number here in the upper left-hand corner is the atomic number. That's the number of protons an element has. So, copper has 29 protons. Lead has 82 protons. Gold has 79 protons. So these are the periodic table of elements. Each of these are elements. There's like 118 that we see right here, 118 different elements. The alchemists thought there were 4 elements, the 4 natural elements: earth, air, fire, and water. Well, none of those are actually on the periodic table of elements. None of those 4 natural elements are actually elements at all. Elements are now known to be pure substances that cannot be broken down further chemically. If you take air and you break it down and separate it, air is a mixture of oxygen, nitrogen, carbon dioxide, water vapor, and trace elements. If you separate air down into the simplest substances you can have, if you break down all the compounds in air, you would have elements. So in order to turn copper, atomic number 29, into gold, atomic number 79, we would have to add 50 protons into that nucleus and an abundance of neutrons in order to balance out that element, because the neutrons help make the nucleus stable. That cannot happen in a chemical reaction. Chemical reactions involve electrons, not protons. To get gold to become, or to get lead and change it into gold, we would have to get rid of, it looks like, 3 protons from lead. You can't get rid of 3 protons in a nuclear or in a chemical reaction. You can only do that in a nuclear reaction. So in fact, it is possible to turn other elements into gold, but you need a nuclear reaction. You need to slam protons. We would need to slam 50 protons into the nucleus to turn it to gold. We would need to remove 3 protons from lead in order to turn it into gold. So why don't they do that? The answer is it is extremely, extremely expensive process. If we take other elements and try to turn them into gold by changing the number of protons in a nuclear reaction, the value of the gold you would make would be far less than the cost it would take to run that type of experiment. Now, if somebody can figure out a way to do it cheaply, you have figured out a way to make yourself very, very rich. That's called transmutation. It's called artificial transmutation when a scientist tries to change the number of protons in a nucleus. Nuclei change on their own, transmute on their own. That natural process is often called radioactivity. Why is it possible for some nuclei to be changed into others? Well, the same way that the number of electrons an atom has, the octet duet rule, influences its chemical stability, the nucleus also has stability, and it depends on the ratio of protons to neutrons. So when we talked about adding 50 protons to copper, we would have to add a lot of neutrons to try to hold that nucleus together. If a nucleus is unstable, it can change on its own. And we talk later this year about how nuclei undergo changes on their own. Why are we talking about all of this? Well, it was the goal of alchemy to change ordinary base metals into gold or silver. Alchemists tried to do it via chemical reactions. We now see that chemical reactions involve the electrons, which are not in the nucleus. Electrons orbit the nucleus. Only in changing the number of protons in the nucleus can we turn one atom or transmutate one atom into another. Changing the number of electrons by chemical reactions will not change the identity of the atom. It just changes who the atom is bonded to. Alchemists did not know anything about nuclear reactions. They were not discovered until well after 200 years following the days of alchemy. Alchemy ended in the really latter part of the 17th century, earlier part of the 18th century. It was about 200 years until radioactive reactions, nuclear reactions, were actually discovered. Changing one atom into another, as we mentioned, is called transmutation. Through transmutation, atoms can be turned into gold. It's just too expensive to do it. So now we know why the alchemists failed in their task, yet they were successful because through the efforts of alchemy rose the subject of chemistry. Notice the similarity: alchemy, chemistry. The word chemistry comes from alchemy. And the alchemists contributed much to what we now consider to be modern day science. They discovered some of the new elements. They discovered elements. They didn't know they were elements. They discovered the properties of acids, if you remember. They started to really dive into the scientific method, to actually have a strategic approach to experimentation. They developed laboratory procedures and laboratory apparatus that we still use today. And the alchemists were also the first to record what was taking place during their experiments. They began to develop the first laboratory journals. They just wrote it in a way that only they could interpret it through the use of symbols and drawings. This concludes our notes over 1-7. If you have any questions on any of these 3 videos, don't hesitate to ask during our Zoom sessions, or schedule an office hours appointment, or email me and we can get together. Thank you so much.